So I'm Dimitris Kiritsis. Now this is the last session of the day. So it will be we have 4 distinguished speakers to discuss the way towards materials and manufacturing ontologies and systems. So we will start with Professor Arild Waller, who is our host today from the University of Oslo. He will talk about, as you see in this slide, system ontologies and IMF. Then we will have Michela Magas for innovation and industry commons. And then we have 2 experts on materials ontologies and manufacturing ontologies, Emanuele Ghedini and Barry Smith from Buffalo, Emanuele Ghedini from Bologna, and Barry Smith from Buffalo University. So, Arild, please come here we want to hear you. And then, will be short presentations, and then we will have questions and answers and time for discussion. Thank you.
So, thank you, Dimitris. So, I'll start with. So, is it this? Yeah. First, some reflections around the phrase ontology commons. So, ontologies is. I will not need to say much about ontologies in this context, but I want to say that it is complicated and specialized, and very few people are able to make good ontologies. Maybe it is a project that, in principle, will never end. Commons has to do with ontologies taken into use. If we develop an ontology and just put it online, it's not thereby commons. It has to be adopted and deployed in order to be said to be a common. And in the context of materials and manufacturing, this means industry commons. I think the idea that once the academic researchers have built top-level, mid-level ontologies, and then the industry will mobilize and make all the classes that they need underneath that. I think this is very naive. I don't think that will ever happen. I think to succeed and to really make ontologies common, we need to pay much closer attention to how the industry operates. And the first point to make is that the industry seeks solution to its problems, and by a solution, it means a solution of the whole problem. And by a problem, it is something specific that you can point to, and where a solution will give some kind of improvement that you can quantify, implement and quantify. So a lack of common language is, in most cases, not the whole problem. It's in many cases, it's part of many problems, but it's very rarely the problem. So to move forward, I think we need to understand better the complex context in which the industry operates. And we need to understand then the principles and mechanisms. And here are some. First, reuse of repeatable patterns. These repeatable patterns, they have many names. So some of them are design code, component, datasheet, product type, package. There are many. There are others. The essence is that there is something that is has a name and some kind of more or less clear meaning. You you select, or the engineers select those patterns, then typically they are configured and instantiated. And this process of configuration, I've seen cases where this can, can be viewed as going through a decision tree. And this is a process where ontologies are very useful, really very useful. So configuration through classification, I noted. And then the concept of system is extremely important. So system thinking. Now I am in the department of informatics, and to understand system thinking is reminiscent of what we do when we teach our students recursive problem solving. The point there is, recursive problem solving is about solving a problem by solving simpler versions of the same problem and combine the solutions. So that is about identifying which simpler versions to focus on. That will be the repeatable patterns. The combination of the solution, that would be system interfaces. Then you sort of are in a system world. And but the hard part is to understand how to think, which very often means to solve another problem than the problem you started with, a bigger problem. And there is the whole practice of the engineers will come into play. So the way forward, I think we need to be clear that it has to be a division of labor between people in the research community, academia, which has sort of the knowledge and the patience and the stamina to make ontologies. That's why ontology design sort of is well suited as an academic discipline. Whereas the industry has a focus on making short-term impact and organize its resources to accelerate that impact. And this urgency that the industry has, which academia lacks, can help us focus on the real problems. So ontologies can give semantic precision, which is important. But this uptake from the industry will require something else. It will require, think in terms of languages, a syntax that is easy and quick to learn, quick to use, and the pragmatic principles that can reflect practice. Pragmatic is about how to learn the language, and this is about being able to capture and support and improve the practice. So, in my title, the acronym IMF was mentioned. This is a project that Sirius has been involved in together with industry. IMF stands for Facility Asset Information Modeling Framework. This is very much an industry-driven project, and it doesn't work the way that an academic project would run, whether you would start with making everything precise and evaluate it and then try to apply it. This comes from the opposite direction, trying to join with large industry projects, understand and try to improve piece by piece how the practice is, and then gradually evolving with an understanding of what the language could look like, a useful language could look like. And this is the sort of example of a syntax which is very graphical, as you can see, and that the engineers can easily relate to. We also have an idea of what an ecosystem could look like, where to the left is would be the ontologies, the class libraries, which sort of is underneath everything. In the middle is something called the type library, and the types would be trying to capture what I call the repeatable patterns. More complicated, really small models. In a class library, you are interested in all relevant distinctions and making those precise. Types are really the patterns that you want to reuse, and you don't want more of them than you really need. And then to the right, you see the real ontologies, and they are there. That is the formal interpretation. And this is where we want to use reasoning and all these techniques that sort of come in the semantic technology toolbox. So IMF is sort of our project to try to respond to these challenges and try to make ontologies industry commons. So I think that our understanding of how to make ontologies, I mean, the community has worked on that for many years and reached, a high level of sophistication. But our understanding of what it takes to make that into practice, I think still is very much in its infancy. Thank you.
Thank you, Aaron. Please don't go too far away from here. So Michela, please come. So Michela will, she is the founder and the director of Industry Commons Foundation, and she will try to present us what is the role of ontologies in industry commons and in required innovation. So Arild presented a little bit the scene of where we want to go with ontologies in industry. Please continue with industry commons, and then we will go deeper in materials and manufacturing ontologies. Thank you, Michaela.
Thank you, Dimitris. I will talk about the industry commons, which obviously is the overarching concept we mentioned also earlier, and also its relationship to this idea of the founding of materials and manufacturing commons. And we have the industry commons, we have OntoCommons, we have materials and manufacturing commons. This word commons is being used to the point where we might wear it out. So I thought that it might be useful to perhaps disambiguate with some of the concepts of the commons that have been used widely in the last few years, in the last sort of 50 years or so. In economics in particular, this word has been used a great deal. It can actually confuse the issue when we start to explain what we are trying to do with the commons. First of all, the traditional models of the commons as used in economics have been derived from systems where land ownership was the primary power structure. So a very different model. During this, in this model, land is allocated as a limited resource to the commoners for use. So it's a finite resource, and therefore it creates an economy of scarcity, and it stimulates particular types of behaviors. And this has been criticized a great deal in economics, and all sorts of models have been derived from that, which I would argue are rather sort of reductive and simplistic in terms of the understanding of what commons are or what commons can be, particularly because the actors in these models are stripped of agency, completely stripped of agency. So I quote Nobel laureate Elinor Ostrom on this, and she criticizes these models such as the tragedies of the commons or prisoners' dilemmas, which many of you will be familiar with or may have heard of. And she says, the observer frequently wishes to evoke images of helpless individuals caught in an inexorable process of destroying their own resources, basically highlighting that there are particular types of behaviors that are described with the framework conditions that are offered by these limited resources and by these types of power structures. So industry commons actually looks at the commons as being made of actors who have agency. So one of the main requirements of the commons, as we understand it in the OntoCommons, industry commons, materials and manufacturing commons, are the commons where actors have sufficient agency in terms of data sovereignty, decision-making powers, and distributed governance. This is the first thing to really distinguish from the previous models. And the other observation is that in these previous models, as they have been described, particularly, as I say, once again, in economics, nothing is mentioned of the unique contributions of the individual actors. They're never described in terms of their domain specialism, their knowledge, or any unique qualities that they may bring to the table, for example, resources or innovative approaches. And of course, if we look at working across domains, we have different knowledge that comes to the table. And if the group needs all of this different knowledge in order to operate, then cooperation becomes a necessity, and therefore it's an essential quality, which is why I would say that cattle grazing, as it is quoted in those models that have been criticized by Ostrom, is a very poor metaphor for spaces for knowledge exchange. And industry commons is very much a place for knowledge exchange. And bringing knowledge from different domains is therefore essential for common incentives and motivations. So completely different behaviors that result from this. So how do we then progress from something that we know as enterprise integration, which is trying to combine all the different systems in one enterprise, to ecosystem integration? I touched upon this before. I will emphasize it again because it is really important. So once again, we need to be sufficiently transparent to allow effective decision-making workflows. Technologically harmonized, this is what OntoCommons allows us to do, and these approaches that we're discussing here allow us to do, but also effectively supported by responsible societal and environmental parameters embedded in the system. So if we look at what our system then looks like, we have interoperability as the key factor, and OntoCommons as being central to this, supported by a series of systems of agreements. This could be regulation, this can be industrial contracts, but this can also be, for instance, intellectual property tracking within the system, asset management. If you're interested in those aspects, on Friday we will be presenting some of the latest breakthroughs that are a result of us taking the OSES, the OntoCommons ecosystem, into an innovation action with big industry where we've had some breakthroughs on this front. Systems of resilience, so environmental sustainability. If any of you are familiar with Kate Raworth's donut economy model, for example, she sets a ceiling for use of materials and resources that is matched with responsible use of resources. So there are economy models that can actually set those ceilings, and we can actually respect that if we embed that into the system. Now, if you're interested in systems of resilience, we also are developing now, as a follow-up to the IP ontology that will be presented on Friday, also a resilience ontology, which will have many aspects embedded in it. And this is also as part of this innovation action. And then, of course, we have systems of responsibility, responsible AI, ethics, etc., and systems of beliefs. So once again, if we have societal values as the foundation of our system, we can incorporate equity, we can incorporate inclusion into our system, in the sense that we can start to monitor data provenance, data biases. Every single data is biased. And for example, we have already had accepted by EOSC proposal that we would match FAIR data, which is a technical connectivity, with just data researchers or data owners, where a researcher aims to be judicious, unbiased, safe, and transparent in terms of annotating data sets, creating knowledge about the data that would allow us to understand inherent biases or provenances or any kind of inherent risks. And then, of course, we build breakthrough innovation on top of this, and we can model future market possibilities based on a system that has all of these components embedded in it. Now, This may look like a system of systems that's traversing all of the different, each one of these horizontals, of course, traverses all of the domains. But actually, how does an ecosystem like this actually take the system of systems ideas forward? Well, if we look at the model of system of systems properties built by Weichert, Panetto, and Molina, the industry commons ecosystem adds certain values to it. So where in system of systems, each component has autonomy, but it is united by a super purpose of the whole system, this autonomy is now enhanced, for example, with cognitive twins and with elements that allow us to model dynamic states. We can have greater modularity and adaptability in it. Belonging to a system is decentralized, and it being decentralized is not a hindrance. In fact, it is a practical solution for all of the different stakeholders who need to store securely their own assets and their own data. Of course, the market competition is balanced by the super purpose and, of course, encoded in the social dimensions, as mentioned earlier. Connectivity here is not just a series of nodes and synapses. We are considering connectivity in this ecosystemic approach as all pervasive, and therefore we can start to build value systems in multiple dimensions. It is a multidimensional system. Diversity of capabilities is not only tolerated or approved, but is actually encouraged, because if we have diverse components that are open towards the system for modeling, then we can model new market scenarios or new use cases. And therefore diversity is welcomed, and we have identified in previous pilots that diversity between the different domains allows us to identify breakthroughs in the gaps between, let's say, in the junctions between the verticals. And emergence is closely monitored as it is in the system of systems, but here it is actually really designed to be trackable throughout the ecosystem, so that we can detect breakthrough innovation, we can have this informed decision-making and investment and resource allocation. So how does this synergy then play out, providing that we have interoperability layer firmly in place with OntoCommons? How does this synergy between in what industry commons can offer and what materials and manufacturing commons can offer play out? Well, to begin with, in order to model, for example, Green Deal use cases, we need both. We need all of the information about all the available materials and products so they can be modeled together with the things that the industry commons bring from other domains, such as environmental and framework conditions. We also need access to materials manufacturing commons data for procurement of most suitable materials. On the other hand, we also can do lifecycle management of the materials and products through the tracking of data and product passports, for example, from industry commons. In order for those to work together, data standardization, of course, is paramount. It's being discussed a great deal here. One thing that's particularly emerged as being important, it would be a top-level metadata standardization in order to traverse the whole space. And then the decision-making processes can be really enhanced by the materials and manufacturing commons about the best performing or most resilient or sustainable materials and products, and they can allow direct route to industrial suppliers for industry commons stakeholders. And industry commons stakeholders can enable the materials and manufacturing commons to connect and interoperate with, for example, a legal commons or an environmental commons, so that we can monitor environmental conditions for industrial applications. So that's all for me now, and I'll pass it on to the next person.
Yes. Thank you very much, Michela, so for highlighting this, let's say, very important need to see the other dimensions. So the environmental dimension, the legal dimension, so also the societal dimensions in data sharing and decision-making using data. Now we will go to these two domains that are subject of the OntoCommons project, so the materials domain and ontologies for materials. And then Barry will talk about the manufacturing domain and ontologies for manufacturing. Emanuele is the main creator of the MO ontology, materials ontology, right? Yes. And Barry is the main creator of BFO, who is the basis also for manufacturing and other ontologies. Please, Emmanuel.
Sorry, I need to be close to this.
Is it possible to zoom in?
To what?
Okay. Okay, so I will talk about how to represent ontological materials, at least under the perspective of the EMMC, so European Materials Modeling Council. In fact, in 2018, several European practitioners in material science expressed the need to develop a knowledge framework consistent with scientific principles and methodologies to complement the existing physical and mathematical approach, and this led to the creation of the EMMO ontology. So the first conceptualization effort that we started to work with in this field suggested that there is a hierarchy of entities that constitute materials, and this is how we represent them. And there is also a particular pattern or ways in which the models used to describe these materials are usually used in particular type of workflow. But please don't underestimate models, because here models is not something separated from the material, but a model here is a physics equation. So it is exactly what we know about the material. So it is what the material is in a way that is much more deep than what we can understand or infer from our senses. So following this first conceptualization, we realized that it is possible to use very specific models, like, for example, electronic models based on quantum mechanics to describe all the entities at every scale, or we can use model more coarse-grained, like continuum models, if you want to focus on entities, but if you on macro scale entities. But if you want to really create a comprehensive ontology for materials, we had to be able to cross all these potential scales in order to be able to conceptualize all the possible objects that we experience in the world of materials and the world of engineering. So this first conceptualization suggested out that if you want to deal with materials, you have to deal with the structure and with the data. So you have to represent the materials in their actual structure. So how they are connected, how their parts are connected together. So how they are structured by using concepts coming from physical science, chemistry, material science, and classical and quantum mechanics. And beside that, beside the representation of the material entities as they are, we have also to represent how we extract data from them. So how we observe them and how we create the numbers that refers to them, and also the methodology. So how we create this number, by modeling, by experiment, which device, and so on. So structure and data are the two things that we need in order to represent the material. So given this first conceptualization, we decided to go the hard way. So let's start with what is the fundamental idea in physics. In fact, there are some ab initio models used in molecular dynamics that use fundamental interaction between, for example, a proton and an electron in a hydrogen atom. So we were forced to go into this direction by developing an ontology that is atomistic using elementary particles as atom, and also that consider the fundamental interaction that comes from the quantum field theory. So we started by introducing in the ontology the atomistic concept that are used, that are the fundamental building blocks that constitute everything that is can be declared in the MMO. But besides a taxonomic representation of the fundamental entities, we need also to represent the mechanism, so the relation between these entities. So we also included in the ontology the potential interaction that comes from what we know about the most fundamental forces. And we created also we merged mereology and causality together, creating an axiomatic system in order to be able to capture the laws or the rules that are at the basis of physical system. In this way, we are, in principle, at least according to the standard model of particle, represent the physical structure at every level. Because even at the macro level, the interaction are the sum of interaction that occurs at elementary level. So we can represent in the MMO the fundamental phenomena, like, for example, the quantum scattering, Bremsstrahlung, the pair production, and so on, and use this fundamental structure as a way to describe how two things interact together. So let's make an example. We can start with a non-quantum example. So let's consider a black box, which is a fusion reactor on the left. Then let's zoom mereologically. We can state that a fusion reactor is made of a plasma and a confinement and a shield. And we can declare, using the MMO ontology, the fact that there is a stream of photon, which is the radiation that heats the shield, or that there is a stream of neutron that goes to the shield and breed the tritium, for example. And this can be declared in the MMO as a stream of real particles, and you can use classical fields in order to reproduce mathematically what you are declaring here. Then, if you're not happy with that, if you want to understand exactly where this radiation came from, you can mereologically zoom again, and then you can declare that the photon comes from Bremsstrahlung radiation, and just also like that. So you know that there are parts in the plasma in which this phenomenon occur and generate a real particle that goes out of the plasma. Or you can represent the fact that the shield is heated by atomic excitation that is caused by the photon generated by the plasma. But if you're not happy with that, then you can zoom even more, and then you can represent the Bremsstrahlung phenomena using a Feynman-like diagram approach, in which the quantum field emerge. You have virtual particles that transfer the forces, and then you are forced to use quantum mechanics in order to represent this fundamental interaction, in which the interaction is transmitted by forces that do not respect the balance of general relativity. So in this way, we can justify or represent entities from the macro scale from the macro to the micro scale, and we can stop whenever we want, because there is no need for us to declare an entity by enumerating all the quantum components. There is no need. We can encapsulate the relation in macro relation that simply say that there are photons coming from one object to another without being forced to declare the fact that each single photon that travel from one entity to another, for example. Then, starting with this fundamental interaction, we were able to build a material taxonomy, which is not only a taxonomy because there are some actions that force these classes to be declared with very specific interaction between their parts, that goes from the fundamental level up to the macro level. You can see we go from the physical particle up to the mesoscopic, the continuum material, and then we open the way to the possibility to declare materials according to their size, function, structure, and so on. But you will always be able to go down in scale up to the fundamental level. Then you can use your physics up to the fundamental. Besides that, we also developed an approach that we call a multi-perspective approach, in order to represent also the data that are connected to the materials. In particular, I don't want to spend much time on that, but we represent in the MMO, we represent the material as a bare entity without so simply a structure of elementary particle. And then there are a mechanism in which we connect data to a physical entity according to a particular semiotic process that specify the methodology used to declare such a data as related to a particular entity, like, for example, density or conductivity for a particular material. So concluding, we developed a merocausality theory that can represent material in a strong physics-based approach rooted on quantum field theory and relativity. At the same time, we can deal with subjectivity using semiotics in order to declare data that are subjectively connected to a particular entity, using, for example, a model or an experimental technique. This theory is for sort of logic, but is ready to use in OWL2DL in a limited version. It can represent executable modeling workflow. It is DCAT compatible. It provides a powerful way to represent properties, and it also has an embedded metrology vocabulary that represents the ISQ, so the International System of Quantities, and the International System of Unit. So the conclusion is that materials ontology should go beyond simple taxonomies and list of metadata to be useful for material scientists, at least according to the experience of the EMMC. And that's it.
Thank you very much, Emanuele, so for presenting the fundamentals of representing knowledge about materials and go to the meaning of data. Now, what we do with manufacturing, we transform material to something functional, so a Ferrari, for example, or an engine of a Ferrari. And Barry will tell us how this knowledge can be represented with ontologies as well. Thank you. Thank you.
So I was very pleased with the last talk. I'm optimistic again about the EMMO.
Yes.
Okay. I'm no longer part of Europe. As some of you may have noticed, a couple of years ago, English people were allowed to leave. So I shouldn't really be at this meeting, although I noticed that there are other non-Europeans here, which is kind of good news. But also, I am European once again, since I now have a visiting position in the University of Italian Switzerland. Now, that is part of Europe, I think. Now, what I'm going to talk about now is what might seem to be the non-European roots of the Industrial Ontologies Foundry. And we'll talk about the Industrial Ontologies Foundry again in the course of this meeting. But today I want to talk about some historical questions. And so I'll also be talking about BFO later on. But here we only need a very small part of BFO in order to see the history of the Industrial Ontologies Foundry. Basically, we need material entities, we need attributes, functions, for instance, we need information entities, and we need processes. And I'm going to talk about aircraft manufacturing because I did a project on aircraft manufacturing with the American Air Force Research Lab. And there we distinguish between entities made of materials such as aircraft and tails and so on, attributes of those entities such as cracks and faults and so forth, information entities such as flight debrief reports, and then processes, design process, production generation process, logistics process, and so on. So let's go through the processes first of all. So the Air Force has an assessment. It decides that it needs, according to its strategic guidance, all of these are processes which are going on in organizations like the Air Force all the time, that it needs new capabilities. And so a material development decision is made that a new kind of aircraft will be built. This is a document. And this leads to a whole series of other documents as the consequences of this decision are addressed. What are the risks? What would be the manufacturing processes which would be needed to be brought into play in order to produce the aircraft, and so forth. So these are all documents about what needs to happen. And now there comes a point where the aircraft is actually built, and then we have sorties. And for that, we need sortie plans. And for that, we need a sortie plan generation process. And we need the actual sortie, and we need the mission which the sortie is part of, and so forth. So we have documents in blue, and we have processes in orange. And now we put various perspectives together. So if you're working for the Air Force and you have data about Air Force manufacturing and about Air Force operations and about Air Force disposal of old aircraft and all of the other things that the Air Force needs to have, then you need to have the possibility of bringing the data from each of these kinds of data collecting processes, data generating processes, material generating processes, and so forth. You need to be able to bring them all together in order to perform all of the things that you need to do with those data relating to the strategy of the Air Force, the inspection of the aircraft, the design of the aircraft, the production of the aircraft, and so forth. So what we did for the Air Force Research Lab was we built a system of ontologies which would allow documents, processes, material objects, and attributes to be brought together in the form of data in such a way that the ontologies would all be interoperable with each other. So this is the same picture again. So we'll go through it. We have documents which are prior to the manufacturing process. Then we have the manufacturing process steps, including disposal, which is the end of life of the aircraft. And then we have operations, which are down there in blue, which are based on plans, which are written down documents. Now, what we're interested in here today is the product life cycle, which is what happens in manufacturing. You start with the design, you go through the plan generation process, then you have the production process itself, and then you have the maintenance process, then you have the use process, which is actually flying sorties, and then you have the end of life process. And these things are linked together by documents. So the production plan generation process has as its output a production plan, which guides a production process, which then leads to a product. A maintenance plan generation process has an output, which is a maintenance plan, which is guided by the maintenance process. And then we can put those together. So now we have the three levels: the product life cycle, the documents, and the product. And there's a constant toing and froing between these different processes. And here we get to the closed loop idea. In the closed loop idea, all of the data that you collect about use of the manufactured product are then cycled back to the design process in the next generation of the same manufactured product. And this at the bottom then is all the material things which are involved in the product life cycle at the top: the people, the buildings, the transport, the repair, the wastewater, the telephone lines, and so on. All of these are material things which are being used by the factory which is manufacturing the aircraft, which is then sent out to be used and maintained and then disposed of. So these are the material things. And now the history. So all of this was done between 2013 and 2016. The Air Force wanted a system of interoperable ontologies dealing with the product life cycle, the use, the maintenance, the documents, the data, and so forth. So we created that. In 2016, Hedy Carré, who is, I hope he's in the room. Hedy Carré visited Buffalo, and I ignored him. So I had a colleague with whom he was working anyway, and to my shame, I only got to know him at the very end of his visit. And he made one suggestion. Knowing the work that we've been doing with BFO in biology and medicine to create the OBO, the Open Biomedical Ontologies Foundry, he said, why don't we create an industrial ontologies foundry? And I had a eureka moment. And I said, that's a really good idea, Hedy. Why don't you stay in Buffalo for another 6 months? And instead, he said, we need to talk to Dimitris. And so immediately I made contact with Dimitris. And then in Lausanne in 2017, we put shape to was it 16 already? We put shape to this industrial ontologies foundry. And then CERN, who is also here, who is also not European. Well, Dimitris is European, but CERN is definitely not European. CERN then turned the Industrial Ontologies Foundry into an effort of NIST, which is the National Institute of Standards and Technology. And from there, it has grown and is now, it's firmly anchored in a number of continents. And given that we have Dimitris and Hedy in this room, not to mention me, I think we can say that it's somewhat firmly anchored in Europe. And that's the end of the story.
Thank you.
Thank you.
Thank you. Thank you very much, Barry. And so let's have a discussion. So please, speakers, come closer to that, to here, because you may have to answer questions also in the micro. But let me start. So what we heard in this session. So we have materials that are at the basis, the foundations of what we have. So also in this room, the computers that work or not work, or the cars, etc. And we have material scientists, nuclear physics scientists like Emmanuel and others, that they design the materials to meet some properties. And then we have manufacturing with all these processes, from the machining to logistics. Also, if you go to the life cycle, that they transform this material to something functional. And if you put together these functional elements, components, so you have products like cars, etc. Of course, this has to, all this is a world, is a complex system of systems. So that has business applications, financial applications, legal applications, societal implications, and all this has to talk together by using some commons, as Michaela said. And to make it happen, we need to do it in industrial environments. And in industry, we don't have ontologists, we have engineers, and they have their own language, and we have to help them to create whatever they create in industry. So there are innovative and creative people by using data that are shared also in this kind of common system. So, and we have all these initiatives so far. So in Europe, we have all the OntoCommons, for example. We have OntoCommons because the European Union recognized the need to use this data in a commons way. And we have the story, we hear the story of Barry, that we have IOF, which is international level, and also based at least in the US now. And we have the chair of the IOF, so Jim Wilson. I don't know if he's still here, but he will be talking in a couple of days also. And we will exchange with him. So here we are now. We are in the process to create some commons. So we talked in the morning about the heterogeneity of data. So the maturity of the systems that we are developing. And my question is what you are feeling, what is your understanding about the next step? So we are where we are. We have some achievements. So if I take the OntoCommons, I believe that we produced beyond expectations, given the level of maturity of the systems that we work. So what do you think? So what is the next step? So to go towards this creation of commons with all the complexity of the system. So do we need more industrial efforts? It is time all these things to be industry driven, to be taken by industry. Do we need still more research? So Ariel said that we need still a collaboration of academia, research, and industry. So do we need to address heterogeneity problems? Do we have problems with languages? So what would be the next step to go together? What do you think, Pali? So you
didn't mention AI.
Yeah, this is, so in the morning we talked also about knowledge graphs. In IKEA, they built knowledge graphs in their own way. And then they apply AI there to have some, also Bosch, they did a very good work. So how to combine knowledge graphs and machine learning. So there are steps there. I personally believe that AI, so including ChatGPT, so may let's say provide good results. if the data are made available in well-structured knowledge graphs, which in their turn are based on ontologies. This is my conviction, my point of view. But so what do you think? What is the next step? So go directly to AI or?
So I'm assuming I'm talking
Can you hear in the online? So I don't know.
Everyone can hear me.
It's better to be here. So yes.
So, the dream would be that ChatGPT could produce good results rather than bad results if it was somehow guided by well-curated knowledge graphs along the lines that Dimitris just described. The problem is that we have too few people, and they have to be built and checked by people to build those knowledge graphs. All of my students get jobs immediately when they graduate. Some of them get jobs before they graduate. The starting salary is $150,000 a year. Now, that's because there are too few students who can do this work. People who can do this work are rare, and so we can't solve the ChatGPT problem by building good ontologies unless we have people who have the training and the talent to build good ontologies. That's a real problem.
So we are here, as I said, where we are. What is the very next step? So what we should do? So do more on IOF. So what we do with the results of OntoCommons. So we have the OntoCommons ecosystem. So what's next? Yeah.
I've got a question for you, Barry. I agree wholeheartedly. I think this is the major problem. And you see it in evolutionary terms, it's an issue about cultural transmission. How do we train these people? How do we get people trained?
Can you repeat the question? You will repeat the question.
So the question is, how do we train the people? I guess I should know the answer to that question. First of all, philosophers are sometimes good at this, but most philosophers are not. I mean, philosophy students. Most philosophers are not good at this because they're not interested in it, because it has a practical application. And philosophers don't care about practical application. Some non-philosophers are good at doing it, but it's a very specialized talent. It's not the kind of talent that any student can acquire by doing enough exercises. And I don't have a simple answer to the question. I have a controversial answer to the question, which is that if we were all doing this in the same way, and I'll talk about that later in the week, then we would at least spare some waste of resources, because all the ontologies that we build would be interoperable with each other.
Should be.
Would be if we all did it in the same way.
Thank you. So
what happens if you pick the wrong one?
Nothing ventured, nothing gained.
okay. Thank you, Barry. So we have one, let's say, next step. So education. So educate more people that are able to work and put this forward. Then, Emanuele, so you mentioned in your talk that we have this SEN workshop which is a first step to go towards a kind of standard for materials ontology. Is that correct? And
Not exactly.
yeah, my question is also for CERN, for NIST. So in IOF also we try to produce ontologies that we make them available, and in view of becoming a kind of standards, de facto or ISO, or we have already ontologies that are standards. I have BFO, for example, and others are coming. So that Sam, you wanted also to say something before, but what do you think? So we are in a way to develop standards for ontology developments or for ontologies that will take into account all what happens today, or we will create many standards as usually, and then we will have to manage the standards that we create.
It would be good if
Can you come here?
by the way,
I just asked ChatGPT what is a car in the airport, and it says independent continuant.
What is it?
It says independent continuant.
What was the question?
What is car in the vehicle?
Well, that's the correct answer.
so,
So it gets one thing right.
yeah. So it's already already trained for people. So I mean, I think I heard a lot in the roadmap about the need for standardization. So of course, a lot of ontologies have been built in the OntoCommons. So it would be good to, standardize those ontology and make them interoperable and connected, such a way that it's easy for people to use them together rather than, piece by piece. So, and IOF is of course one of the platform for doing that. Of course, if you are willing to align with the BFO at this point, at least.
And Emanuele, you think that this, let's say, effort of standardizing somehow, or the discussion at CEN of material ontologies, or other material ontologies, could be, let's say, developed in line with what happens in IOF, for example, with manufacturing ontologies and similar things? I mean, should we try to launch this kind of process?
The CN effort that has been pushed by EMMC and EMCC, the Characterization Council, were in the direction of providing a terminology.
Two different bodies, this one. Yeah.
Yes. To provide, to define a terminology, in order to be able to talk about modeling and characterization in a way that facilitates the common understanding. So it is not about standardizing an ontology for materials. It's about to understand each other in terms by using particular terminology. So that's this. I think
so
is.
We need to start with the terminology first.
I think we need to start with the best practices.
Okay.
So I don't think that standardizing an approach to word conceptualization is a good way to proceed. In fact, OntoCommons approach is about, okay, you can have your view of the world based on Dolce, UFO, Baffo, MMO, whatever you want, but please provide bridges between the views so that we can reuse on, say, the same thing in a different way, so that also other communities that have a different view about how to represent the world can use what you did. In my presentation, I show that how the MMO is rooted on what things are for a physicist, for an applied scientist, which for us is the truth, but it's not always like that for the people. Sometimes I look at things, even if they're not made of elementary particles, but using other type of lenses, social, emotional lenses, and so on. So that I have another ontology in my mind, which is not the MMO, dealing with something else. So so that's why I don't think that there is the standardizing an ontology for a particular domain is good. Standardizing the practices, like we are doing in OntoCommons, is something that can be useful.
Okay. And also, I think when let's say Ferrari orders to a material scientist, engineer, to design a material for a particular specification, they are not interested in the quantums or the photons or the neurons, not at all. They are interested in some macro level characteristics of material. Okay, so yes, please.
So I said a few minutes ago that I was optimistic about the EMMO once again. Now, something that I hadn't thought about before this meeting, but maybe this meeting will provide the opportunity for something to happen on this front. So for about a year now, we have been working, that is to say, the BFO community has been working on developing a physics ontology and a mathematics ontology. Now, BFO has no place for mathematical entities for a number of reasons. And I've always said to people, well, you don't need a mathematics ontology. You just go to the mathematics textbook and you have your ontology. But we do need a mathematics ontology in order to build a physics ontology. Now, I think that the physics ontology that we are toying with, it's not even a beta 0.0001 version, it's a toy, may be compatible with the kinds of things that Emanuele was talking about today. And so I'm hoping that he and I can use the opportunity of this meeting to work out whether what we're doing, it's a multi-perspectival physics ontology, which covers the same ground that you were talking about a few minutes ago. Maybe we can find a pathway to converge.
Okay, very good. So this is where we are, Sento.
He has to smile now.
Yes, yes. So Arild, so with your experience with working with industry, so in the Norwegian mainly context, so what do you think so far? So we heard your presentation. So what kind of ontology industry needs, and how to use them? So from your experience so far, please come here. Yes. And if this ontology should be standards or not standards?
Yes, so I tried to make the point that we need an ontology which is sort of underneath, which is the the basic vocabulary and the relationships and the ability to check consistency of that. But I tried to make the point that I don't think that this is really enough for industry to take up on. I think they need other entities, which I called the types, but I mean more complicated, more complex artifacts. So I think in order to sort of succeed in getting more industrial uptake, we should focus on to capture the objects that can easily reflect practice and be concerned about them, and not so concerned about precision and completeness of the ontology. I think the urgent point is to get it slowly into practice.
Okay.
Whereas if you build larger and larger and more sophisticated ontologies, I think you really risk to alienate the industry.
Yeah.
Yeah.
But this, let's say, ontologies of artifacts at the industrial level should have roots somewhere in these more fundamental ontologies. They should be linked to that, or there is no need for that. So
Yeah.
there is a need to link to material ontologies at a certain level, or not?
It's a need to do so if you want a proper and detailed semantic interpretation.
Okay. If you want to reason about it.
If you want to do reasoning, which is very useful in many contexts.
Okay.
But I mean, it's more urgent to find for the industry use a proper syntax, I would say.
Okay. Yeah. So more practical language to express
Yeah.
the needs of industry.
Yeah.
Good. So, and then I would like to come to Michele, because the needs of industry, but the industry works in a social environment, in a business environment. So do you think that there is a need also to link commons at legal level, for example, including IP, with what we have in ontologies like materials, so even at the detailed level, or manufacturing at the process level? Do we need to create these links to have access to this information, or just laws and money and profitability and nothing else?
It would be a bit difficult to have money and profitability if you couldn't register your intellectual property,
Okay.
if you couldn't track it and trace it. So it is a similar question to the one I was asked a long time ago, when I think it was British government actually said to me, do you think data is currency? And I said, well, currency has been data for quite a while, so I don't see why data is not currency. But it's one of those things that you can't decouple some of those things. In fact, this is why we have the research fields such as enterprise integration, which we need to actually expand. I think the way that we're working with ontologists here, we're working across domains and with the various different, connecting various different domains in industry, is really encouraging this ecosystemic approach also to enterprise integration. So we need ecosystemic integration. We need to extend enterprise integration into ecosystemic integration. And then when you look at asset management, because ontologies are enabling you to manage assets, one of the things that we will show on Friday, in fact, is how we track directly from the application level, so all of the data instances at application level, how we track it through the domains of, on one side, supply chain via the IOF ontology, on the other side with the new IP ontology. For data reference models for intellectual property, and then connect them with BFO at the top again. So basically, we can do that from now and from every instance dynamically. And I think this helps us to manage, and then if we actually have people from industry in the room, as we have our IKEA colleagues, for example, in the prototyping room upstairs, they are able to react to this immediately. And they're able to say, you know, okay, so now they have a full visualization of the data management and asset management and how this is referenced in the ontologies, and they can actually start to react to that from the perspective of direct applications with users, with their customers, with their supply chains, with their manufacturing. They are, for instance, a great example because they have all of the elements under one roof. And with the new kind of approach to how they manage their customers through knowledge graphs, for example. And they can start to react to these visualizations, and we can develop an iterative process with industry where they say, well, that's useful to us. But you have to first build the prototype to actually show it to
Best
them.
practices that manually.
Yeah, absolutely. Okay. That's what I would say.
Very good. So thank you very much. So I think since the beginning of OntoCommons and since 2016 that we started that, so we made some steps. So we have also some products. I think we have a more clear view, but we are not yet there. So we are increased a little bit our level of maturity, but there is a long way. So before to arrive in commons, not necessarily standards, but in commons, common understanding, I mean. So is there any question from the audience, so here or online? Yes, please.
Yes.
I will repeat the question.
I'm concerned about standards, industry relevant standards. We design products, build assets in accordance with numerous standards. These may be European standards or American standards. To really enable the use of ontologies in building models representing building asset models with reference to the standards they are designed in accordance with. Because we don't want to do something else that something totally different, because the standards are there to ensure safe design. They are there to ensure that products are available for purchase. So there are many reasons why we need to have a representation of industry standard content to build asset models. Isn't that so?
You mean there is a need to have the existing industry standards that you have to respect, that there are constraints for you to develop products? Is there a need to transform these existing standards to ontologies to create models? This is the question. So you are concerned, or? Okay. So this is another dimension that I heard also some time ago, but I don't know where we are now. So is there a real need to transform existing industrial standards of practice to a kind of ontological representation to be used in ontology-based models of industrial assets? Do you have an opinion on that?
I have some
Experience. Yes.
So there are some industrial standards which are way too, I'm thinking of the STEP standard particularly, which are very useful for ensuring interoperability of data, but which are way too complicated in various respects. And they're getting more complicated over time. And the STEP people themselves are wanting them to become simplified. Another problem is that ISO, although it pays lip service to consistency from one standard to the next, it doesn't have people who really understand logic. And so the definitions in ISO standards are not formulated in the way that you would need to formulate them in order to create tests of logical consistency. They're formulated in the same way that dictionary definitions are formulated, namely to help human beings. And so the ideal would be to create a parallel set of definitions in a logical language for all the industry relevant standards. That would be a disaster because then we would see how inconsistent they all are.
The existing standard.
Yeah. So the dream of having logical interoperability across ISO standards would expose the mess that ISO has made.
So the first example that I know about an effort to ontologize an existing standard is STEP, done at NIST some years ago. At least I know a paper about that with the contribution of many Europeans. I don't know if this OntoStep, I don't know how it is called now. Is it used? Is it valid? Or
Say something.
Please say something about that.
It's called OntoStep.
OntoStep.
Yeah, but I wasn't responsible for that, so.
Was or not?
No. So as Barry said, OntoStep, it's kind of just like a translation from the step into an RDF graph, more or less.
Linear to RDF.
Yeah, more or less. It doesn't really consider much of the ontology as we understand today. I think the ontology standard need to capture the requirements presented in the current standard. The problem with the current standard is they are not very context-free. Let me just say that. Standard, it's just, as Barry said, it's kind of ambiguous, and the terms are usually overloaded with multiple meanings. So the ontology need to capture those standards in a contextual-free manner.
This is the problem that Barry mentioned also.
Yeah, because one term just means multiple things.
Also, I heard also that there are some industries, big ones, that they try to ontologize, let's say, standards that they are using, but I don't know. There are no publications about that. I don't know if they are successful with that or not. Yes, please. Yeah.
With a new system, they have to use the data from the old system, new system. It's just, if you actually go into the departments, they're everywhere. So there's clearly a requirement. Now, clearly in these industries, there are lots of standards, but there are not standards helping a lot. I'm actually working on a project at the moment where the manager thinks the standard will help. It'll be interesting to see whether it does or not. In the past, it doesn't seem to help. So there is a major problem about how you, in places where the businesses are more and more automated, how do you manage the data? You've got the existing systems can't talk to one another. The existing systems get out of date. When you replace them, how do you translate the data from the old system to the new system? People don't know the answers to these questions.
Mm-hmm. So this is, if I let's say interpret it correctly, so there is a challenge, maybe not to ontologize the existing standards, but there is a challenge or an opportunity to create new version of these standards that are based on the knowledge that we have and the know-how that we have to create meaningful ontology-based standards, probably.
I think that's halfway there. I'd like to frame it in a different way. I would like to say, if it is the case that ontologies are going to help with semantic interoperability, you've got a test case here, and you can do it by ontologizing existing standards. You can do it by creating
Okay,
standards.
I see.
Do it any way you want. You need to demonstrate that if you use ontologies, that it has benefit in these situations. So there's a problem, there's a clear problem where the rhetoric of ontologies claim to have an answer that's endemic in anywhere, any enterprise with any number of systems that needs to be tested.
So I guess that will be solved somewhat with the combination of ontologies as meta-link approach.
Okay, so yeah, so there is
It's not like it's a fixed problem. It's a difficult problem. So let's try everything. We need to blocks.
best practices. So there is a new field of activity or work that it seems looks interesting in industrial environment. You wanted to say something, Alan?
So I'd like to just comment on this question from Anders from a table on standards. So I am absolutely convinced that to get the uptake on ontologies, we have to be able to formulate standards. And because very much of industry is actually delivering on the requirements that are formulated with reference to the standards.
They are obliged to do so.
Yeah, but I would also say that to make ontology sort of out of standard, a discipline standard, you can't just read the definitions and think you understand them. You need to understand, the whole body of knowledge from the discipline and the practice, and then you can contextualize the definition, which is very few people can do that. And I also think that the notions that you need to capture many of these standards, like the system standards and the system disciplines, use concepts that I think we don't really understand well from the ontology community. They are complicated concepts. But I think to help someone like Anders, we need to provide them with more precise standards. Yeah.
So in IUF, we have a working group that we're working on an ontology for systems and system engineering. So with contribution from various people, including industry. And we are not close to have this done, but maybe a first version will have it in the next months. Let's hope so. So any other question? So very good. So thank you very much. So now I think at least I have a better understanding of where we are now. So in terms of efforts in developing ontologies applicable to industrial domain, materials manufacturing and other systems, etc., which is part of the ecosystem. And in the next...
Sorry to interrupt.
What is the question?
No, he has a talk on this topic tomorrow.
Okay.
But Alexander, let us know if you'd like to also have the microphone open to ask a question. And we will activate the microphone for you. You are on stage, so you can actually should be able to open your microphone.
Alexander, can you talk?
It's already answered. Okay.
I cannot hear the...
No, I don't think you activated the microphone. Okay, just
okay.
If he wants to speak.
Alexander, can you hear us? Alexandru, you want to ask a question? So it seems the communication is not possible.
No, but I think
So in the chat, there is no question also?
no.
No, okay.
No. My talk tomorrow will go into more detail of the topics. It's just a comment.
Okay, it's a comment that tomorrow. So as I was saying, so in the next days, we will have opportunities to go deeper to one or the other of these, let's say, challenges that we discussed today. Thank you very much. So for your patience and the long day. Thank you also to people from like Barry, Jim, Serm. So you look very tired now. So and see you tomorrow. Outside there are posters if you want to. Umut. So please, yes.
Okay.
Just
Don't make
couple of
us
minutes
work
and then we
more.
go.
So summary of today. Today is over. Yes. Yeah, today was morning, of course, dedicated was demonstrators, and then in the afternoon we had first the roadmap discussion, afterwards the highlights from our previous workshop regarding marketplaces, and finally we had the standardization discussion towards standardization in materials and manufacturing domain. And of course, we also learned from Mihaela finally what commons means, and in different contexts. This was also a great addition. And as you all know, there are posters outside and maybe also snacks and things. Yes, so there will be some food. So it's like you can get your blood sugar again up, and meanwhile also look around and discuss with the poster presenters. And wine. Well, there is also wine. So this is yes. Yeah. So enjoy the poster session and see you hopefully all tomorrow again.